Hello everyone and welcome to the Core of Everything, where today our topic is impact craters. We're looking at impacts, shocks and what rocks can tell us about the early solar system, formation of planets and evolution of the geosphere. We need a little help understanding some of these concepts, so we've brought in a PhD student which specialises in geophysics. Ladies and gentlemen, Banusha Kugabalan.
Hey guys!
I'm so excited for our first guest.
Oh, it's a pleasure to be here. Really, I appreciate you guys asking me.
Have you been tuned into any of the other episodes? Or?
Yeah, I have been actually. I've listened to all the ones out so far. Absolutely love it.
Do you feel like you're learning about geology?
I really am.
Wait, would you say you're a geologist?
No, absolutely not.
Do you have steel-toed boots?
What? No.
Do you have trousers that can be zipped into shorts?
No.
Do you have a hammer?
I do.
God.
There we
A
go.
little bit more clutching at straws for a moment.
But no, I'm not a geologist. I'm more of a physicist, I'd say.
So, do you want to briefly explain to the folks at home what your PhD specialises in?
Yeah, so my PhD focuses on shockwaves from impacts and how they affect rocks and meteorites and their magnetisms.
So, essentially, these shocks preserve a record of magnetic fields within the rocks.
Yeah.
Is that right?
Yeah.
Okay.
And I'm looking at how shock from impacts and hypervelocity impacts have an effect on that.
Okay.
I'm going to do some experimental work as well.
Nice. Do you ever look at a meteorite or anything like that? Or
Hopefully.
Yeah.
I'd like to go to like Antarctica or something and pick up a meteorite, but I don't know about funding and that, so we'll see.
Yeah.
That'd be awesome. I've not been. It's top of my bucket list is the moon.
The moon?
Yeah. But I've got to shoot
bucket list,
big.
though.
I've got to
Yeah,
shoot for the moon.
Yeah, nice. Hello.
Yeah.
So, I think we should start with the basics, which is what is an impact, or what do we mean by an impact?
So an impact is simply just two bodies colliding into each other, which results in a very high impulsive force over a short period of time.
Do we know sort of the level of force or anything like that? Or it's just unimaginable?
In terms of numbers, I think it's on like the gigapascal scale, right? Which is, I think you only get elsewhere with nuclear explosions because you see certain geological features that can only be formed by impacts or nuclear explosions.
Right. So these stuff like, or diamonds,
I guess
in
so.
terms of impacts.
One of the big ones is shocked quartz. So quartz is a mineral, and then you can produce certain like deformation in it that shows you have these features.
So why do these impacts happen?
So these impacts happen between space debris and planetary surfaces, moons and asteroids.
I think I remember Mark saying in the meteorites episode, we have essentially you have all the building blocks of the solar system.
Yeah.
That are all like Lego pieces that have been built. Like you say, you're building like the Millennium Falcon or a house or something. I don't know. But whatever's left, either that one piece that's left over, that's your sort of space debris that's just going to crash into each other.
Yeah.
And form create these impacts.
Yeah, so like they're all scattered in space in our inner solar system, and they're all orbiting around the sun, and all these bodies have their orbital paths, and they will cross over. So like a meteorite will cross over the Earth's orbit, and then that's where you get collisions.
Yeah. Okay. So some examples is Tycho, is it?
Yeah.
So Tycho's a really nice one because actually if you go out and look up at the moon, you can see it normally in the southern hemisphere of the face of the moon that we see, and it's that nice big kind of white circle with lots of rays coming out of it. It's about 85 kilometres and 105 million years old. So yeah, it's quite a nice one that you can go out and spot.
So since the early solar system in the protoplanetary disk, matter has been always colliding into each other, causing impact, and that's how the celestial objects we see today are formed in our solar system. And due to gravitational accretion, impacts constantly occurred.
What gravitational accretion?
Gravitational accretion is anything with mass will have a gravitational pull, an attraction that pulls it together and they collide into each other. And that accretion is that process of everything, every crumbling bits in the space just coming together.
Stuck together.
Yeah.
So
and
in that
forming
disk,
one body.
it must have been a pretty crazy environment, right? You
Yeah.
just got stuff like flying around.
Yeah, all the time. And as things were coming together and accreted and forming larger bodies, the debris in that area were getting reduced.
Okay.
And then the solar wind from our young sun blew them away,
Okay.
spreading them out. And then they just started orbiting.
So we've got a
the-
spreading out of material, but over time,
Yeah.
our number of impacts is
Yeah, this is
decreasing.
all over a very long time.
Okay,
Like,
okay.
everything's very slow. So,
Right.
This was like 4 billion years ago, wasn't it?
yeah.
4.5, yeah. But interestingly, between about 3.8 and 4.1 billion years ago, there's been theorized that there was something called the late heavy bombardment, which is kind of this narrow range of rocks that have been dated, particularly from the moon, that we can look at when they were molten, and we think they were molten because they were melted by impacts. So there seems to be this slight increase of impacts around this sort of 4 billion year mark, and that's possibly due to instability of planets and kind of these post-accretion impactors. So as you said, Banusha, this material that's been spread out that is maybe being kicked out of their orbits by instabilities in gravitational fields.
Very quickly about about that sort of 4 billion years ago.
Yeah.
That's around the time that the moon formed. No, was that 4 billion years ago?
The moon formed more like, it was quite close to when the Earth formed, like 4.4.
Oh, sorry.
5.
Yeah, 4.4. So, and that was formed by not really an impact. Well, it was an impact, but not really a crater formed. It was a Mars-sized body hit the Earth, and there's the evidence for that itself is the moon, because the moon resulted from the debris, these bits of Lego that have formed together to produce the moon.
But we can look at the chemistry of the moon and the Earth, and what's in the core of the Earth and the moon, and what's in the surface, and that can help us learn about the timing of this event. So that was sort of 4.5 billion years ago, and the frequency of impacts has been decreasing over time. But are we still getting them today?
Yeah, so impactors come our way all the time. And for an impact to create a crater, it needs to be a certain size. If it's less than 70 meters in diameter, it'll just get vaporized in our atmosphere, and that's how we get meteorite showers. So you'll see like little shooting stars. It always reminds me of X Factor, actually.
How so?
Why?
Because you know the theme tune, like the beginning of X Factor, is an impactor coming into Earth.
Oh yeah, the star,
Yeah,
right?
Yeah.
Oh, yeah.
Oh,
And
no,
it
the
lands
X.
in
Sorry, the
it
X.
lands in a stadium in Manchester
Yeah.
or wherever they're shooting X Factor. It's a massive coincidence, that, isn't it? It's weird.
So it always reminds me of that. But yeah, and then if it is 70 meters in diameter or above that, it will hit our surface and produce a crater.
Okay, so 70 meters is the threshold at which below that it gets vaporized, but above you form a crater.
Yeah.
Great.
And there's been an interesting study actually by some scientists at the University of Freiburg in Germany. They published a paper in Earth and Planetary Science Letters in 2015 trying to predict the number of craters we should see on the surface based on these frequencies that you're talking about. And so they said that above 6 kilometre wide craters, there should be 70, and we've discovered about 70. So basically, we have found all the large craters. But between 250 metres and 6 kilometre wide craters, they think there are 350 undiscovered craters based on the frequency of impactors we should get producing these craters.
But most of these are undiscovered because they're in Antarctica or in the oceans.
Yeah.
Oh, that's a lot. Still lots to uncover, isn't
And
there?
those are just ones at the surface. So there could also be ones that have been buried under, layers of rock.
Through geological time.
Yeah. I thought it was a really interesting study.
Yeah, absolutely.
So what happens when you get these impacts? How do they happen?
So impact cratering are very dynamic and complex processes. And there's so much going on all at the same time. And there's so much going on from a micro scale. We've got shock metamorphism. On a mega scale, we've got loads of deformation. And it can even perturb planetary bodies as well. It's like that powerful that it can
Like shift them into different orbits.
Yeah, it's crazy. Like the amount of, if it's a hypervelocity impact, it has that ability to do that.
It's interesting because you kind of think the planets are just sat there stable.
Yeah, you
not
think
gonna
nothing
move.
can move it, but
Yeah.
an impact can. And there's two types. So there's simple craters that can be formed or complex craters. And all depends on the three stages and how they're made. So there's contact and compression, which involves the projectile, so whether it's a meteorite, asteroid, or comet that hits the target, which is our surface. And the contact occurs until the compression ends. And that depends on the size of the impactor and the velocity it comes in at as well. And what basically happens during the contact and compression time is all that kinetic energy from the projectile gets converted into an internal energy, and then there's still a bit of kinetic energy that's then divided into the projectile and the target. And then from this, that conversion is where the shock wave forms, and that shock wave develops at the interface of both these surfaces and gets distributed through the meteorite or the surface.
So you're basically converting all this energy of this thing that's moving really fast through space, and you're needing to dissipate that energy somehow.
Yeah.
Which I guess big time heat, as well as the shock wave that gets spread out through the surrounding rock.
Yeah. So you get the heat from the shock. So when that shock wave, it's very abrupt and very discontinuous, pressure, temperature, and density-wise, and it just goes through, and it leads into irreversible deformation.
So we've got our first stage is contact and compression. What are the next two?
So the next one is excavation, where all the material in the crater, it starts to form a cavity. So everything, due to the shockwave expanding and dissipating, all the material gets ejected out of the crater.
And these are all happening in really short timescales, aren't they?
Yeah, and it can happen over a long period of time depending on the impactor diameter.
Okay.
So, so when all the material is being ejected out, then you go on to the modification and collapse stage, where due to gravity, all the material that's around the rim can fall back in slightly. And then there can also be, so that forms a simple crater. And then you can get a complex crater where the center of the crater uplifts. So you get like a little W shape kind of crater. And the uplift happens due to the material not having enough strength to fight against gravity. So to reach gravitational equilibrium, it uplifts.
So you get a little peak at the centre.
Yeah.
It's like a rebound effect.
Yeah.
And then the other one was the simple one where you have this ejector from the meteorite that gets overturned.
Yeah.
So the layers of rocks beneath that are all in like stratigraphical order, but then around the rim of the meteorite it's all been overturned in the opposite order.
So
that's pretty cool.
When you have that modification, it's everything in reverse.
Okay.
Because of the
So how do you tell impact craters apart from volcanic craters?
So volcanic craters, like the ones that haven't been blown off, have steep slopes and a crater that's very distinct. But then the ones that have been
I'm just laughing at blown off.
what? It has been blown over. It's like a really powerful eruption.
Yeah.
The crater gets blown off and it looks exactly like an impact crater. And the way to distinguish between them is looking at shock metamorphism of the rocks. So they're very distinct because of the high temperatures. The rocks will have melted. There's microscopic deformation in the minerals. You'll find, if it's a meteorite impact, you'll see iron and like meteorite remnants in the impact crater. So that's how you distinguish between the volcanic and then meteorite impact.
And something really cool I've seen on some planetary surfaces is you get these secondary crater chains, which can form either by, if your impact has been breaking up as it's coming through the atmosphere, you get like this chain of material from all these little bits from the impactor, or you get secondary impacts from when your big impact comes in, throws up and ejects and excavates all this material as you were talking about, and then that material then goes and forms more impacts around the main crater from this little material from the big one that's like been spewed out into surrounding ones, which is quite cool.
So some of the consequences of these impacts. So, we've already mentioned that under these high pressures, sort of crystals and minerals form that wouldn't otherwise have been able to exist, essentially.
Yes, so there's high pressures involved. So you've got 1,000 megapascals to 100 gigapascals. And due to that pressure, diamonds can easily form.
Yeah. We know that diamonds form 100 miles into the Earth. So it's mad to think that just this impact on the surface creates temperatures that equate to or more than temperatures and pressures that are below the Earth, that deep inside the Earth.
I mean, these are, as far as I'm aware, these are the highest intensity process. This is the highest intensity process that we're aware of in terms of pressures and temperatures. Because these things move. If it's similar to kind of meteorites and micrometeorites, they move at like up to 70 kilometers per second, right?
Yeah.
Which is crazy speeds, and when you take all that energy of that thing moving so fast, that's got to go somewhere. Which I guess is why these are such high intensity events. And that, I guess, can you talk a bit about how that energy gets dissipated?
Yes. So when the projectile hits the target, the kinetic energy is turned into internal energies, and then the leftover kinetic energy in both the target and the projectile, that conversion creates a shockwave. That's how the energy is processed, and that shockwave can create plasma processes to occur in the cavity, and the shockwave propagates out of the crater and decays, and it can realign magnetic moments in rocks surrounding the crater. And when the magnetic moments realign, it retains the magnetic field of the Earth or any planet, really. And that's what I look into.
So you have this contrast between magnetism that results from the impact itself and magnetism that was there before the impact around sort of the crater.
Yeah.
Okay.
And so what information do you get from that magnetic signature in the rock?
So the magnetic imprint left in the rock, it tells us the time of the event and the magnetic field. And from that, we can understand the Earth's field or planet's field. And then we can also understand the early solar system's magnetic fields, the protoplanet, like going back in time,
because I guess you were saying,
basically.
Right at the beginning, that we get impacts within that protoplanetary disk as well.
Exactly.
So we can start to understand what's going on in these disks.
Yeah.
Which is helpful because often in astronomy, when we look at disks that are forming planets, they are typically opaque, so it's hard to see what's going on inside them. So it's really helpful to kind of get this information that you're giving us.
I want to talk about plasma.
Oh yeah.
Because you mentioned plasma, and I only know it as the fourth state of matter.
Yeah.
What is it?
So plasma is basically gas that's been heated up to very high temperatures, 6,000 to 10,000 kelvins, and
6,000. So that's about 5,700 something degrees Celsius.
Great mental maths there, Jack.
Definitely done on the spot.
Nice. 5,726 or something. Roundabout.
You definitely don't have a calculator, but yeah.
Order of magnitude.
I'm showing you my. Do you know what I mean?
I am really impressed.
I think the disparity between kelvins and degrees is 273.15 degrees. So yeah.
So good on you.
You're doing really well.
Yeah. Good job.
So plasma
forms
at these temperatures.
Yeah, and you have all these electrons and protons with high kinetic energy, all buzzing around like I always think of wasps, like a bundle of wasps, or like crazy, and that's how they are, the electrons and protons and from ionized elements.
And that can be produced by lightning strikes as well. You get plasma.
Exactly.
You've got these high temperatures ionizing gases in the air.
Yeah, and so when a hypervelocity impact occurs, you have these plasma processes that create a magnetic field itself.
Okay.
And that can affect the magnetism of rocks.
So in this case, we have different magnetic fields that we're preserving. In the crater, we preserve the magnetic field of the plasma. whereas outside the crater we're preserving a different magnetic field,
Yeah.
right?
So outside the crater, you're preserving the planet's field
Okay.
due to shock, and then inside it's due to the plasma process.
Okay.
But that only occurs at very high velocity
Okay.
impact
Right.
craters.
Right.
So, I mean, we have all these impact craters on Earth. And I think you mentioned, was it 350 undiscovered?
Yeah.
Between up to 6 kilometres?
Yeah, up to 6 kilometres, yeah.
So the question, I guess, is what happens to these impact craters over time? Why can't we see a lot more of them? If they're 6 kilometres wide, you expect to see them quite a lot. And I think that's when the geological processes, surface processes, comes into play. So we have, obviously, weathering and erosion. You can have, well, some of them are filled with water, actually, and have forms of lakes and stuff.
Yeah.
But ice itself can wear away at these craters. I think we have an ice age roughly every 100,000 years. And so can you imagine every 100,000 years you have the wearing away of the surface of Earth by ice, that just sort of scrapes away at these craters, meaning that there's no evidence for them.
And there's an interesting relationship between ice and craters, actually, because on other planetary bodies, particularly the moon. So craters are quite good at giving you shadows, and therefore you have cooler temperatures where ice can potentially exist. So there was a study published in Nature Astronomy in 2021 by Honibal et al. And they used SOFIA. SOFIA is basically this plane that flies high up in the air. It stands for the Stratospheric Observatory for Infrared Astronomy. And basically what they do is they point a telescope at the moon and other things. And so we know that there is water in the surface of the moon. We see an absorption band in our infrared astronomy at 3 microns. But this could be, we don't know if that's necessarily molecular water. It could be water locked up in minerals and crystals. But this study found a signal for molecular water. And they think that this water is stored within glasses on the moon, which could be formed by impacts or micrometeorite impacts, or voids between the grains. And this is so that water is sheltered from the harsh conditions on the surface of the moon. And they're finding this because this water is being protected in the craters, where it's not being the sunlight isn't shining on it and evaporating it. And this is so important for solar system exploration, right? Because if we want to go and explore into the depths of the solar system, we need water to survive. And we need to find that water from somewhere. We can't take it all with us. So if we can find it in craters, that gives us a bit of a stopping point along the way to say, oh, here's our water. So I thought that was quite a cool study.
Yeah, that is interesting.
I suppose one thing we need to address is how this relates, or how would we avoid having a impact if we see an asteroid heading towards us? How do we avoid that? And one thing that we covered in the mass extinctions episode is the fact that NASA and a couple of academics at Imperial helped develop mathematics for the DART mission, where they sent a probe, sort of this kamikaze probe, to fly into a asteroid.
Into actually the moon of an asteroid.
The moon of an asteroid, to try and knock it off course. And they did. I think they knocked it off course by a few meters or something like that. But over the course of, a long distance, a few meters becomes enough to help an asteroid move past Earth rather than smack into the dead centre of it.
Yeah, now speaking of mass extinctions, I heard you talk about the Deccan traps. And so the lunar crater in India, that's actually located in the Deccan traps. It's because it's made of basalt. They actually thought it was a volcanic crater for ages. And then only recently, because of looking at the shock metamorphism of it, they realised it's actually an impact crater that's based in the Deccan traps. I thought that was really interesting.
Wow. And that shows that things get quite complex, don't they, when you've got different processes at play.
And so it's got a lake in it now. And I think in 2020, because of the salinity and the alkaline in the lake turned pink just because of the water levels. How cool is that?
Sounds like a really cool place.
Lake.
Maybe this should be added to the bucket list.
Yeah. Yeah, not the moon or Antarctica.
It doesn't fall into the rankings, I'm afraid.
Craters in India.
Yeah.
Let's go.
Yeah, I think there's also the Sudbury basin in Ontario in Canada, which is formed from a meteorite, I think, as well. And that's well known for storing resources. I think it's got nickel in there, and now that's covered also by a lake. So
Does it change colour though?
I have no idea. I have no idea. It's actually bright turquoise.
Oh, that is quite lush, isn't it?
Yeah. I've made that up. Banusha, thank you so much for joining us today. I think you did a really good job.
Oh, thanks, guys.
Thanks for sharing your wisdom, your knowledge, and your friendship. And thank you very much for listening, whoever is listening.
And I think Banusha's been a great example of how geology isn't necessarily just about rocks.
No, it's not.
It's broad, right?
It's way more than that. I've actually really learnt from you guys that, like, I never thought like oil or evolution or even fossils, which is kind of stupid of me, but I didn't realise fossils were part of geology. I thought it's more like an archaeology thing. But yeah, no, I've learnt a lot, and I am actually really glad to be in the geology department doing a PhD.
Wow.
Isn't it? That's the nicest thing you're going to get from me. No, it's been a pleasure, honestly. Thanks.
Okay, cool. All right, bye everyone. Thanks very much for listening.
Bye.
Bye.
Bye.